Okay, today we see the sixth lecture of Harvey Friedman on invariant maximality, and it's the fifth lecture on invariant maximality, the reversal. Please.
Thank you. All right, so the text of the previous lecture 5 is in the downloadable lecture notes page, the text from the lecture, and it's on section, and that was on section 410 of the reversal. 10, the 10, the 10th one, chapter 4. And also the current version of section 4.10 in full is on my downloadable manuscripts page. And as usual, I was a bit late putting these up, but before today at least. So reminding you, we are reversing this statement about maximal cliques in ordered variant graph. Do something here. Yeah. Okay. And that every ordered variant graph has a suitably invariant maximal clique. And that's all part of a big positive theory that we're not talking about now. Big positive theory where I prove these things from large cardinals. All right. And then reminding you the reversal chapter 4 of the book looks like this. And we did this. And then last time we did this. All right. Now, I said I was going to go back one each time. That's a bit of a lie because um, we're going to discuss sections 4.8 and 4.9 because 4.8 doesn't end so nicely for section 4.9. I think it's not worth it me fixing that so it's smooth. But section 4.7 ends nicely or nicely enough for sections 4.8, 4.9. So section 4.7 ends nicely to set up for section 4.8. And you can think of section 4.9 as a continuation of 4.8, really. Although I still believe that breaking it up into 4.8 and 4.9 was a good idea. So let's recall, last lecture we started with the end of 4.9 with a second order structure whose domain is internally well ordered. And last lecture we ended, that's what we started with, and we ended with the same kind of second order structure, but with a definable well ordering of the universe via constructibility, inner model constructibility. Okay, that's what we did last time. Now, today we start at the end of section 4.7 with the structure that's extremely ill-founded. Its domain is actually dense. And the indiscernibles are not C1, C2, whatever. The indiscernibles are 1, 2, 3, 4, dot, 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 the positive integers. And we discussed section 4.8 where we develop particular pre-well ordering in M and stay entirely in the structure M. So we stay entirely today in the structure M. Then we discuss 4.9 where we use the pre-well ordering where we use, there we are, where we use the pre-well ordering from 4.8 and related machinery. And that related machinery is what makes the break not so clean. To get to the end of 4.9 with its second order structure whose domain is internally well ordered. Okay, so at the end of 4.7, which is where we start today, we see 4.725. There's a structure M whose domain is the non-negative rationals under the usual order and a k-ary relation. R within discernibles 1, 2, dot, 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 where less than is the usual ordering in which the following holds. First of all, there's tupling. So getting tupling is a thing that's in the earlier parts of the reversal, and actually is not that straightforward. It's a little bit tricky. All right, so but the tupling here that we're assuming is that we get here at this point of the reversal is just for k minus one tuples. If you remember, k is a big number fixed at the beginning of the reversal. And we get a unique p greater than max x such that R of px. And the reason we get that is because we set up our master order invariant graph, which at this point is hidden, is in the past, so that this kind of thing happens. All right. So actually, this is not such um, this is not really a 1-1. You'd like it to be 1-1. That is, if you have two k minus one tuples with the same p, the p is unique, but with the same p that they're equal. But we won't get that. This is all a bit subtle, having to do with the early parts of the reversal. Instead, we get something weaker, that if x and y have the same max, that if they have the same max and the same unique p, then they're equal. So we really only have a 1-1 encoding of a given max. This is a subtlety that we have to handle. It has some interesting implications. All right. So, and also this unique p is always less than the indiscernible n if the max is less than the indiscernible n. All right. By the end of 4.7, that is in 4.725, we actually have a pretty good form of limited separation. Uh, First of all, L of k is the full predicate calculus on a k-area relation symbol with less than. Equality is irrelevant because it's defined. We only want to apply this language in obvious linear orders. Okay, so uh, if E is definable over Q of 0Q, that means the interval left 0, right open Q made of rationals. If it's definable, then it's of a particular basic form, set of Q U semicolon M for some U in 7 tuples. And I'll explain what this construction is. This is the only slightly troublesome thing that doesn't make the transition, that makes the transition slightly not perfect between section 7 and section 8. That is, that at the end of section 7 here, we actually have this concept used. Okay, we'll come back to that. But you can see this is a kind of separation because it says that no matter what quantifiers connectors, whatever you have, it can boil down to something very explicit. This being very explicit with 7 parameters, by the way. Now, in regular set theory with separation, you know that an arbitrary formula is cut down to something, a simple formula with 1 parameter, right? With a 1 tuple, namely the set of all x such that whatever that's actually equal to y is equal to the set of all x such that x is an epsilon, such that x epsilon y. Uh, and the parameter is y. because it's a set of all X such that X is a member of Y. See, the parameter is Y, just a one tuple in regular set theory. Here, there's seven. I need seven parameters. All right. Now, finally, indiscernibility. So this is a fairly simple thing: tupling, limited separation, and indiscernibility. So if I have now, this language, if you remember in the early lectures on the reversal in the front, before we decided to go backwards, I had this finite language. K1 means 2 to the K, it just means one exponential. Uh, 2 to the K variables, complexity 2 to the K, and the K-ary relation symbol, and always less than is understood. So this is a finite fragment of L of K. So, and by the way, along the way with separation, I only had separation in various restricted forms. I mean, even parameterless, all through section 7. I had these restricted kinds of separation with maybe without parameters and also maybe with only this finite language. Uh, and then I had to actually develop and prove that I had this, you see. And that's section 7 is pretty elaborate. And of course, that's what we're going to do the next week from now. All right. So given a formula in this finite language, and I have two sets of indiscernibles, two sequences of indiscernibles that I'm using, and they're order equivalent. The indiscernibles are order equivalent. The indiscernibles are these positive integers in the structure. Um, and then I have parameters below, any parameters below, these are rationals, of course, parameters below that we have equivalence with the statement. The statements are equivalent. And I can even move the top less than n and less than m. Oh, what's less than n mean? It just means that I'm quantifying all the universal and existential quantifiers are quantifying over all the numbers less than n. And here they're quantifying over the numbers less than m. You see, so yeah, so these indiscernibles are less than n, and these indiscernibles uh, are less than m. Then you can move these to these. You see that? So that's the natural indiscernibility you want to do, with bounded quantifiers. All right, now this set Q0M construction is a construction of a subset of Q0Q to the M with parameters U in here. That's low level in L of Q. See, I don't want to give all the details of this, but it's sort of low level in L of Q. Uh, L of Q, it may involve M. You see, there may be there may be some big, so it isn't quite in this language here, down here. Um, and this language appears in the beginning of the reversal, as I told you, as a finite language. Okay. Now set Q0M is the following technical low-level explicit construction. Let Q be greater or equal to 0 and U be a 7 tuples. Set is the set of all X, just to give you an idea of how explicit this is without getting a lot of details. It's the set of all X such that R, the atomic relation, the relation R holds of pair code star X, comma U star K. PC star, it's required that Q be greater than or equal to 0 and U be a 7 tuple. PC star is an explicit way of coding tuples of standard length by ordered pairs. See, ordered pairs come up in here. We want to code by ordered pairs. Later, we're going to see that we want to code sequences of ordered pairs by ordered pairs. Various things come up. Standard length by ordered pairs. Star K extends by repeating the last term to get the length K for application of R. Yeah. So we talked about this some time ago. This star K notation is to stretch a bunch of stuff to have length K so I can meaningfully apply R because R is a K area relation. All right, now section 8 starts and it's called internal pre-well ordering. The point of this section 8, 4.8 is to create an important pre-well ordering and some machinery associated with the pre-well ordering. Because remember, uh, in section 4.9, which we're also doing today, in section 4.9, we want to continue with that pre-well ordering, armed with it from 4.8, in order to get this second order structure that is well ordered. That has whose domain is well ordered. Yeah. All right. So we continue to work in the structure M, which is the non-negative rationals with the carrier relation Rn, these indiscernibles, and we develop the M internal pre-well orderings and their fundamental properties. This is in preparation for section 4.9, yeah. And at the end of 4.9, we get this, which is the start of last week's lecture. Yeah, this thing here. That's the end. All right, so we need some notation. Def of Q semicolon M is the family of subsets below Q, which are subsets of things below Q, which are L of K definable over Q0 K Q less than an R. And def is the union of def less than Q is the union of the def Q prime, where Q prime is less than Q. Yeah, and def M is the union of the def F of Q and M. Now, we will want to use separation and indiscernibles to show that this big def can be pulled down into little defs. In other words, defs with a Q in there. Various things like that. Yeah. All right. So in any context whatsoever having nothing to do with this reversal, there's a notion of prelinear ordering. It's a binary relation, which is now this is reflexive, transitive, and connected. My notion of linear ordering is always irreflexive. All right, so prelinear orderings are reflexive, transitive, and connected, and the field of a relation is the set of coordinates of the ordered pairs in the relation. And xty means t of xy and so forth, the standard notation. It's important to realize that this is not, that the equality relation may not be identity, as x is equal ty if and only if xty and ytx. Yeah. And then we have less than t of x, and we have equal t of x, and we have less than or equal tx, and greater than or equal. Yeah, did I put them all around? Maybe I repeated some. I don't know. All right. All right, close enough. All right. The inverse of a relation is just reversing the ordered pair. And again, having nothing to do with reversal, some terminology. If I have two prelinear orders, if I have two prelinear orderings, a relation between field, the first field and the second field is called a partial isomorphism if certain obvious things hold. Um, it's, but the main point here is, I mean, it preserves the relation. T and T prime are preserved, but the main point here is that should be remembered is initiality. That is, uh, the domains and the ranges, oops, are closed downwards. Domains and range are closed downwards as required to be a partial isomorphism. Now, a full isomorphism is when the domain of V is the field of T, or the range of V is the field of T prime. So uh, it's the whole thing into something, or it's something into the whole thing. And an isomorphism between them is when the domain is everything and the range is everything. Sometimes we want to treat partial isomorphisms. So partial isomorphisms are relations. They're not really functions necessarily because the equality relation may not be the identity, right? So the partial isomorphisms we treat as, we think of them as functions, even if they're multi-valued, where all values bear the equality relation in the target prelinear ordering. Uh, yeah. All right. So plop of Q is the set of all pre-linear orderings whose field is a set of pairs. You see, this comes up that I have to do pairs. It's a little hard to explain easily why this keeps coming up, but the field is pairs, not points, and T is definable. So T has to be Fourier, right? Because if it's a binary relation on pairs, it's a Fourier relation. And plop of less than Q is the union of the plop Q prime where Q prime is less than Q. And plop is the union of the plop Q. So these are the prelinear orderings. Uh, I forget why I put it. Why didn't I write PLO? I think it's PLOP. I had a reason for that. Okay. W plop and W plop of Q and W plop of less than Q, these are the ones which have a well-foundedness condition, namely that every non-empty subset of the field lying in def2, because remember the field is a bunch of pairs, lying in def2 has the least element. And you remember def means definable with bounded quantifiers, but it could be high up, way high up, much higher than Q. So we aim to prove that any two W plop have the maximum isomorphism among those that lie in def4. The isomorphisms, the partial isomorphisms, obviously are in def4. I mean, that we're interested in are in def4. We want to show that there's a maximum one. We know that for T in W plop of Q, T itself must be tied to Q, right? I mean, uh, T is a relation. I mean, a plop, but T must be well-founded with respect to arbitrary, limited, definable, non-empty sets. So we need to start using indiscernibility actually to get what we want. So let Q be less than N and T be in plop Q. The following are equivalent. T is well-founded. Every non-empty set of field T lying in def less than N semicolon 2 has a T-list element, and then even more specifically, every non-empty one of these set constructions, these explicit constructions, set of QU2 contain the field of T, U is a set of parameters, sequence of 7 parameters, has a T least element. So, in other words, if you're a little bit well-founded, then you're completely well-founded, meaning well-founded with respect to everything that's definable with bounded quantifiers way up high. Here, it's definable with quantifiers ranging over something less than n. And here it's some explicitly constructed thing with where 7 tuples can be used below n. And this is a technical thing, and as is this most of this section, it's proved using the indiscernibles and the separation. Next, suppose I have 2 of these W plops, well-founded things, and V and W are partial isomorphisms, which are definable. Then the domain is either the field, the whole field, or some initial segment. The range is either the whole thing or some initial segment given by a point. This is very much like it would be in just regular set theory, except we're inside a structure and we have to be careful about definability, the notion of well-foundedness. Right. 1 and 2 hold with V replaced by W. Yeah, we have just a second one, of course. The fourth thing is that if X is in the domain of V, then V of X is the strict sup over T prime of the Vy prime, where Y prime Tx. Here's the abusive notation where I'm treating partial isomorphisms as actually functions, even though they're multi-valued. If X is in domain of V, implies W of X is the strict sup over T prime with a W Y prime with Y prime T X. Yeah, I'm just saying the same thing for the second one. Yeah, there's nothing here that I'm really doing. Okay, but also these 2 partial isomorphisms agree on their common domain. This is all to be expected. And V is contained in W or W is contained in V if you have this situation. The 2 partial isomorphisms. Yeah, and V minus 1 is a partial isomorphism between going the other direction. It's still definable. Okay, so this is kind of straightforward. Now, if you have 2 of these well-founded things and F is a partial isomorphism between them that's definable, then F is some set is explicitly constructed from 7 parameters less than n. And for this, use M indiscernibles in limited separation. Because all you know is that the partial isomorphism is defined maybe upstairs somewhere with bounded quantifiers. So then how do you get it to be low level? Well, that's handled almost entirely by limited separation. But an M indiscernible is needed for this to make sure that we can keep everything below n. All right. Next. Next is what we're aiming for in terms of comparability of these W plops. there's a partial isomorphism that's inclusion maximum among those lying in def 4. It in fact lies in def less than n4. And exactly one of the following holds. It's an isomorphism all the way, or it's total on the domain, and the range is all the stuff below a point, or the vice versa. Uh, and F is a full isomorphism. That's just the definition of full meant either the whole domain or the whole range was used. Okay, and this is all from what we had. Now, we want to get comparability, right? So we have two of these well-founded gadgets. Comp of a T prime is the inclusion maximal partial isomorphism from T prime lying in depth 4. And it lies, in fact, in depth less than n4, meaning that uh, the place at which it's defined and lives is below n. And it's also one of these things, set Q's at U4. All right. Now, this gives us, this basically gives us a very useful uh, well ordering. And we're going to use this. Uh, we're going to use this as our main well ordering, as our pre-well ordering, namely less than or equal W, less than W, and less than and equal W are going to be the relations on W plot as you'd expect. Okay, namely, how would you compare them? Just in the obvious way, according to the nature of the maximum partial isomorphism. All right. Now, if you have two of these well-founded gadgets, and comp is a full isomorphism, that's all from clear, but also less than or equal to omega is a prelinear ordering, as you'd expect. And uh, and isomorphism is equivalent to being less than or equal both ways. I guess this actually does require proof, which I give in the manuscript. All right, so all of this is highly expected. Uh, Now, every one of these gadgets, every one of these well-founded gadgets below n is less than W something below n. And this is very easy because you can put something on top and there'll be plenty of things that you can use to put on top that you know that are okay. So and you will stay below n. I mean, n is easily seen to be highly a limit. That's not a problem. But you can actually, yeah, do that also. We now define specific elements of W plop n, which are strict soups of W plop less than n under less than or equal to W. So we do have these well-founded gadgets or well-ordered gadgets, but we care about how high they are, so to speak. So if you look at all the gadgets, if you look at all the gadgets that in W plop less than n, they ought to, in some sense, their order types, in some sense, should reflect the number n, the indiscernible n. That's the idea here. So we define T star of n as the relation on 8 tuples given by Q1, U1 is before Q2, U2 if and only if Q1 and Q2 are less than n, U1, U2 are 7 tuples. The 8 tuples come from the fact that we have one more argument Q, right? where set of Q1 U1 4 is less than or equal to sub W of set Q2 U2 4. And T star of n is given by uh, uh, making this on ordered pairs, X and Y. So you see T star of n is a relation on A tuples, whereas T star of n, T sharp of n is the corresponding relation on ordered pairs via the pair code, the pair coding. All the different kinds of pair codings and all this stuff, codings of tuples, all that stuff is is the core is very much heavily part of section 7, which is next week. And we won't use T star. We'll use it only in the proof of the following theorem below. Uh, PC is an explicit way of coding tuples of length less than or equal to k minus 1 by a single ordered pair, introduced in the beginning of section 7 based on tupling. And to give you the idea of the form it takes, PQ is a pair code of P1 through PM, if and only if R of P, P1 through PM star K. See that this is the old, this is the thing we said at the outset of coding. Remember, tupling was called tupling right in the beginning of the talk. The pair code is unique by tupling, yeah. All right, so the following holds. These TNs and T star Ns are definable. Let's see, T star N, I guess T star N was on 8 tuples, wasn't it? Yeah, and that's on ordered pairs, so that's in 4. T star N is a relation on 8 tuples. In and 16. Okay. Now here's the point. T star of n is well founded with respect to def 8. Yeah. In other words, all the definable limited quantifier, bounded quantifier, definable sets have least element. They have to be sets of A tuples because of the nature of T stars. And T star of n is in W plop of n. T star. Yeah, T star is the one with the big arguments. Yeah. All right. If T is in W plop of less than n, then T is smaller than T star, T sharp of n. Yeah. So this is the point. The point is that this is kind of like a strict soup. This thing here is a strict soup of the T in W plop less than n with respect to less than or equal to W. This is the key point. All right. Get this from direct calculations. Now we're in section 4.9. And so we have the structure of, this is the structure that we began with last week. This is the second order structure. We construct X, an internally well-ordered structure with domain D, linear ordering less than D on D, a three-area relation pair on D, a second sort set of subsets of D, unary predicates U1, U2, and so forth on set, and constants C1, C2, and so forth from D. Epsilon is a standard membership relation between elements of D and elements of set, as we did last week. We will define the endpoint, but it takes some effort to properly define this thing and improve some basic properties of it that we used last week. So we define the endpoint codes. So the whole point is this is supposed to be a sort of a something definable in the structure capital M, right? So we have to define the endpoint codes of D and capital D. And we have to define the M set codes of subsets of D. Okay, I haven't defined D yet, have I? Yeah. Okay, I'll show you what that is. All right. We show that every non-empty element of set has a less than D least element, and the soup form 2, and the ternary relation pair on D. And then we introduce the language. Okay, so I haven't really told you what, and then there's a language for this, the language of X, the language of everything I'm building right there. Yeah, so D is the set of all equivalence classes of the equivalence relation equals W. So we have the well-founded gadgets, W plops. We have these suitably well-founded gadgets, and we have the notion of isomorphism between them. The equivalence classes are the elements of D, just as you'd expect. So every element of D is an element of W plop, right? We write D equals square brackets T, where T is in W plop, and D is less than DE if and only if there's a T in D and T prime in E such that T is less than WT prime, right? And D is less than or equal to DE if and only if the same thing with T less than or equal to WT prime. Okay. So we now have this is the well ordering of the new domain that we really want. But then we have to actually show that we get a suitable amount of indiscernibles and separation from here by reducing it back to M. Okay, so less than D is a strict linear ordering on D. It's irreflexive trichotomy and transitive. Namely, it's the less than W relation on these well-ordered gadgets. And D is less than or equal to DE if and only if D is less than DE, or D is equal to D. Less than D has the least element, 0. Every D in D has an immediate successor. These are all straightforward. But we also have endpoint codes and M set codes. The endpoint codes and the M set codes are A tuples. The endpoint codes of D and D are the QU, such that set of QU4 is a member of D. Remember, the elements of D are these W plop guys, and those are well-founded relations on two tuples, on pairs. So they're sets of 4 tuples. The M set codes of A contained in D are the QU such that A is the set of all D and D such that some element of set QU8 endpoint codes D. See, we ratchet it up in good instead of to go from points to codes for points to codes for sets of points. You see, codes for a set of points is the set of all is is a set of codes such that the original set is a set of all D and D such that some code endpoint code something endpoint codes D something in the set. Okay. So the phrase M codes refers to both M point codes and M set codes. And these codes are always from 8 tuples. We say that a tuple is below P if all of its entries are less than P. And set is the set of all subsets of D with an M set code. That's clear. That's clear that we want that definition. U of N is a set of all subsets of D with an M set code below N. And we use interval notation for the linear ordering less than D. For example, square bracket 0D, right open, uses a notation like this, right? Okay, so every D and D has an endpoint code. For all N, there is a less than D, least D, and D with no endpoint code below N. This unique D is an endpoint code below N plus 1. See, so in this setup, that's a very important place, namely the least D in the domain with no endpoint code below N. Okay. That's going to be like our new indiscernible. The nth indiscernible when we pass to this internally well-founded structure. Okay, and that's proved using limited separation and the T sharp N construction that we did using D equals using that place in the new domain, square brackets of T sharp square brackets N, sharp N, sharp tuple N, braces, no, whatever. Okay, so we officially define C of N is going to be our nth indiscernible as a less than D least D with no endpoint code below N. For A contained in D, we write A is less than D if and only if everything is smaller than D, and A is much below D if and only if there's an E below D, such that A is below E. Okay. Now we have the following lemma. C of N has an endpoint code 1 higher. These C's strictly increase, just what you'd expect. Every D in D is less than D sum C of N. And that's clear. C of N is a limit in C, less D. That's going to use a little bit of a very modest amount of indiscernibles. And now we have U1 is contained in U2 dot dot dot, that they're a hierarchy inside set. In fact, the union is everything. Oh, what and we define U of N, that's very important. Whereas I should have emphasized it. Where is that definition? Just a second. Let me find it. Ah, here we are. U of n is the set of all subsets of D with an M set code below n. See, that's very important. U of n is the set of all subsets of D with an M set code below n. All right. That's where we were. Okay, we have the following. C of n has an endpoint code. Okay, we were already doing this. We already see each C of n is a limit from the indiscernibility. Yes, here. That's clear because of the definition of set and the definition of U of n. That's completely obvious. Uh, Now, for every q less than n, there exists a d less than c of n, such that every e less than d with an endpoint code less than q is less than d. And that I think that requires the indiscernibility to prove that. You get that. And if A is in U of n, then A is much below C of n. Yeah, in the definition of U of n. 6 is the least straightforward, and that requires M indiscernibility to do that. Uh, okay, so we get well order and non-empty. We get soups and non-well and well ordering from this. See, we built this thing out of well-founded parts, and so therefore the well-foundedness gets inherited. Now, we have to address pairing. So we define the linear ordering less than sharp on D. Uh, this is Lexmax, really. This is lexicographic order when the two things have the same max. And the M point codes of X in this is a multiple form of stuff we already did. The endpoint codes of X are the tuple of X of a tuple of an M tuple are the M tuple of endpoint codes. And the M set codes of a subset of D to the M are the QU such that A is the set of all X in D to the M such that some element of set QU2 is an M point code of X. A partial pairing is a bijection that does what it's supposed to in this building of a pairing function on capital D, not the old situation with positive rationals only, is a bijection that works up to a point. And F has an M set code, which also has an M set code. And we'll identify functions with their graphs, which in this case are ternary relations on D. All right. If E is non-empty, then M and has an M set code, then E has a less than sharp least element. That's clear because Lex Max is going to be kind of well-founded. The well-foundedness is inherited. All right. Now, suppose I have a map F from less than sharp D1, D2. Uh, so this is a set of pairs that's Lexbacks below this particular pair, D1, D2. Then less than the initial segment up to D, into the initial segment up to D. And G is something similar with primes, be the partial pairings respectively. Then F and G must agree on their common domain. And there is at most one partial pairing with a given domain. This is clear from the well-foundedness of the situation. All right. If D1 and D2 are below Cn, if F is a D1, D2 partial pairing, then F has an M-set code below N. Okay, use limited separation and discernibles for that. And let D1 and D2 be below Cn, then there's a unique D1, D2 partial pairing. It has an M-set code below N. Yeah, so this is what we were aiming for in order to get that. We wanted to get these uh, we want to get these partial pairings on the domain D. Remember, the domain D consists of equivalence classes under isomorphism of internally well-founded pre-linear orderings. Okay. All right. Now we get some more technical things with regard to these partial pairings. Remember, these partial pairings are initial segments of the pairing we're looking for, uh, which preserve max-lex. So if we take the union of all these things, pair, that this is uh, this is what we want. And we have to, and we have the theorem that proves that the theorem to the effect that this is actually what we want. This is the bijection between D squared and D, which preserves less than sharp, which preserves max-lex, and pair maps 0 Cn squared into 0 Cn. Okay. This completes the definition of the structure X equals D less than D pair set epsilon U1, U2, and so forth, and C1, C2, and so forth. And we usually treat U of N as a subset of set rather than a unary predicate on set. And then we make up a language for we make up a language for this structure X, a two-sorted language of the obvious kind, which doesn't really require any explanation. But I mean, this is what it is. And we define SAT as usual. An M assignment is a tuple. An M assignment is a tuple which handles the first M constants, M first order variables and the assigns to them, and the first M second order variables are assigned. And then we want to transfer back from statements made in this new structure X. We want to transfer it back to M. So we actually, for this purpose, we actually need something a little bit more. We need something a little bit more refined actually, namely SAT when we put less than D and U of N on top. And that means that the first order quantifiers range over less than D, and the second order quantifiers range over U of N. Okay, so we have notation for the fragment, for the language fragment, L of X and M. And uh, we have the notion of assignment. And this is just a general an adaptation of the definition I gave before. We have SAT of M, phi, D1 through DM, A1 through AM, less than D. This means the first order quantifiers range over below D, and the second order quantifiers range in U of N. Okay. Uh, Now we have this lemma. This is a very technical lemma. Let me see if I can explain this point. You have any D below C of N. I want to be able to find Q less than Q prime less than N, bigger than N minus 1. And these are going to be super high in N, and they're going to be obtained by using indiscernibles. The point of Q is that uh, everything in C1 through Cn minus 1 has an endpoint code below Q, and uh, and also every D prime less than or equal to D has an endpoint code below Q. Okay. And then we need to know that a whole bunch of other stuff, several other things, when true upstairs, actually have a witness below Q prime. If you're looking at stuff below Q, there's some related things that if they exist at all, are going to be below Q prime. That's what this is about. Uh, and you can always do this because you can argue that we know that they must exist below n by some sort of indiscernibility. We know that, and then they must exist below a q prime that's below n by applying a clever use of not so clever, straightforward use of indiscernibility in back in M. Okay, and we call so this q prime is really this pair Q prime is called critical for D if and only if this lemma holds for that Q and Q prime. Okay, and then we have uh, a theorem about how we can use this machinery in order to convert formulas in M, excuse me, in W, the new structure, back to formulas in M. And so there's stuff like this that's needed. Uh, so that basically the notion of SAT, this notion of SAT in the new structure, quantifying the first order quantifiers less than D and the second order quantifiers in U n minus 1, uh, that this will be defined, this whole thing will be defined over Q0 over Q prime, where Q prime is still below N. Q prime is below C of N. Uh, no, so below N, the indiscernible N. And Q prime, remember, was one of these things that was picked that was very big with uh, big enough to do witnessing below Q because these materials are below Q. Uh, okay, so from that we immediately get limited separation in X. We get that if D is below Cn and phi is a formula in L of x n minus 1m, and D1 through dm is below D, and A1 through am are in U of n minus 1. See, all the things in UN minus 1, they have codes. They're coded below n, well below n, all of them. And that's important for this. Then the set we're looking for is going to be in U of n. See, it's important that the set of, if you use parameters below D, first order parameters below D and second order parameters in U of n minus 1, then the set you get defined over X, the new structure, is going to be in U of n. U of n. Okay, and that's the kind of separation we want. Now, there's a similar thing you can do for indiscernibility. For indiscernibility, we need to know that this correspondence between statements made in the new structure X, going back to the corresponding statement in M, that preserves manipulations on the subscripts. You see, you want to go from the indiscernibility, you want to go get the indiscernibility for X from the indiscernibility that we already have for M. And we do that by examining how we go back and how it preserves the combinatorial structure of what we're doing, meaning in terms of the indiscernibles. So reviewing the M indiscernibles, this is M indiscernibility that we're assuming right at the beginning of today's talk for M. If you remember, the indiscernibles are these numbers, A1 through AJ and B1 through BJ. We're assuming that they're order equivalent and positive integers, and we have parameters below these things. These are rational parameters. Then we can make these statements and use less than n and less than m. And here's the version we use for x. So here's x indiscernibles. We have a formula, again, with living in n minus 1, because, and m is the arity of what we're doing. And we have an order-preserving change of the I less than R, for which C of I or U of I appear, staying within R through n minus 1. Then if we make that change, we get equivalent truth values. If we just make these subscripts or indices, so to speak, moved in an order-preserving way. Now, actually, we get complexity. Now, remember, complexity k of 1, which is 2 to the k, which is much bigger, is what we had for indiscernibles in M. So we actually get complexity with at most k of 1 divided by 100 times M, which is, because M is smaller than or equal to k, which is going to be much bigger than k. So we're okay with this. You see that 100 times M blow up comes in. Where is that? 100 times blow up here. When we went from formulas in X back to formulas in M, there was a blow up of 100 times, not just 100 times, but a blow up of, see, this is complexity T, but 100 times the number M of which is the arity of what we're doing, the arity. Then, but that's harmless, you see, because We can do this that way. And so we wind up with this theorem, which is where we want to be, which is the start of section 410, which we did last week. And this is just a copy of what we started with. And you see the limited separation. Uh, the indiscernibility is for complexity less than or equal to K. Yeah, now you remember the first thing we did in section 10 last week is to get rid of the K using a compactness theorem. This is from last week. But this is where we started and this is where we end today. Okay, so I hope you understand the big picture at least. I know this is highly technical and and has been worked out in great detail and will be checked even further. But we are going from we're starting from with a structure M with its indiscernibles and tupling and its separation, and we create this second order structure and with a horrible ill-founded domain, sorry, over here. And we go to a well-founded domain here in this second order structure, and we have tools to go back to this. So the separation and indiscernibility we get in here are derived ultimately from what we got in here. Uh, and remember, D is the set of equivalence classes of an internally well-ordered relation. That's what this is all about. This 4.8 is to prepare us for D less than. That's important. Uh, yeah. And then, of course, this stuff we did previous weeks. All right, Andreas, I'm done.
Yeah, thank you.